Hi, my name is Ashish and I work for the chemistry content team at Byju's. So I was wondering, how do I start today's topic? I'm going to talk about thermodynamics. So I asked a couple of my friends, what should I talk about? How do I start? And my friends thought he was smart when he said that, hey, you know what? Take a piece of paper, burn it live on air, and that's thermodynamics. Although that's kind of correct, it doesn't serve the purpose of what I want to do. And it's, well, not the simplest of examples, you see, because a natural process is actually really complicated if you want to learn it right from scratch. So what we'll do, and what we usually do, is we eliminate all possibilities and we start from things one step at a time. So let me start with something you guys really want, some kind of tips for exams, and I can't stress on this enough. You must be well rested before a test. I know this sounds like something that everybody tells you, but this is the most important part. Well, you must absolutely not study one night before the exam. Make notes. I've made notes for this session. You see this? These are papers I've made for this session actually. This really helps you. It gives you confidence, It makes sure you don't forget stuff. And if you do, you can always look at the piece of paper in front of you. Well, not in an exam, but this is always helpful. So stay well rested. Do not take stress and give it your best shot. Results are not so important. So I'm going to get started now with the actual thermodynamics. That's what you're here for, right? So I'm going to talk about this from the point of view of chemistry. What exactly is thermodynamics? Well, thermo means something with temperature, heat. Dynamics is flow of heat, specifically. That's what thermodynamics is, flow of heat. What is heat? Very philosophical idea. But in layman's term, heat is the energy that exists when there is a difference of temperature. You say that heat flows. So the necessary condition for heat to flow is that temperature must be there. There must be a temperature difference. I know this sounds like I'm taking very small baby steps, but these are the most important ideas. You see, if you have these basics right, then you can solve the most difficult question. And of late, especially in the JEE advanced exam, a lot of questions have been asked on these theoretical ideas. Sure, you have a lot of numericals that you can solve, but I'll leave that to another day. For now, my focus is the basics. So back to thermodynamics, right? Flow of heat. I explained what heat is. Heat is something that exists when there is a change in temperature and then heat flows, from a high temperature to a low temperature. If this is confusing, think about what happens in physics. You have current. Why does current flow? Well, current flows when you have a difference in potential from a high potential to low potential. Similarly, high temperature, low temperature, heat flows. Okay, so we're clear about heat. What on earth is temperature? Another philosophical question. But in layman's terms, temperature is basically the energy possessed by any body. Now you see, at any temperature, even at the room temperature or the temperature of AC right now is 24 degrees Celsius, everything has some energy because atoms inside me are vibrating and they're moving around. So this is the energy that I'm talking about. This is called internal energy, right? You already know all this. So if the temperature increases, the internal energy increases. You know where I'm going with this, right? The first law of thermodynamics. We figured heat, we figured temperature. Now let's get to work, literally. So what does the first law of thermodynamics say? Well, let's use a good old example. I have some gas in a cylinder. Now I decide to heat that gas. There's a burner underneath it. Now when I do that, what can happen? Notice that I said can happen, not does happen. Temperature can increase. It doesn't always increase. Keep this in mind. Think of some examples if you want to. On some case where I heat something but the temperature doesn't change. Think phase change. Anyway, back to our example. I heat something, its temperature can increase. And if it's a gas, this example that I had in a cylinder, the gas can expand. So basically, work can be done by the gas when it's expanding. So I've said that heat, Q, is equal to, it can increase the temperature, which I said is equivalent to increase in internal energy, right? So that's equal to delta U plus, what else was left? W, which is the work done by the gas. This is the first law of thermodynamics, basically saying that energy is conserved. Remember, this is when there are no non-conservative forces. What are non-conservative forces? Well, things like friction, basically, they don't exist. Wait, you guys, some of you may have caught on to this and you're thinking, what is this dude saying? How is this the first law of thermodynamics? First law of thermodynamics is that delta U is equal to Q plus W. What did I just say? I said Q is equal to delta U plus W. Okay, what I just told you is how thermodynamics is taught in physics. And this is my biggest bone to pick. Chemistry and physics are the same. They're not so different. Thermodynamics is the same in both of these things. That's the point that I'm trying to drive home. How's that? Well, you see, I spoke about work done by the gas. Yeah, when I gave you the equation to be Q equals delta U plus W. What's so different in chemistry? You see, let me tell you how first law of thermodynamics is taught in chemistry. Well, you say that the focus here now is the internal energy. How do I increase the internal energy of a system? It's two ways, right? Listen carefully to this. I have 2 points to drive home here. I can heat the system in such a way that it cannot expand. I fix this cylinder, in the top part of the cylinder, and I heat from the bottom. So now it cannot expand. So what happens is, the only possible thing is that the internal energy increases because I've heated it. So that's one way. Now the second way is to increase the internal energy in the same way using a different thing. What do? Well, I make the entire thing adiabatic, which means that I don't let heat escape. Okay, so I have piston. Now the piston is movable. There's a frictionless piston. Why? Because I cannot have any non-conservative forces. That's important still. So I push this piston down, and now, because there's no heat exchange from this, which is my system, my gas and the surrounding, so the only possible thing is for the internal energy to increase because the temperature increases. So you see what I did? I increased the internal energy in two different ways, either by only adding heat or by doing work on the system. If you've been paying attention, you'll realize that I said on the system now, I said by the system there when I was talking about physics. That's what's the biggest difference. Anyway, more on that just a second. So we got this equation. From this you get that delta U is equal to Q plus W, where this W now is the work done on the system. Okay, so what was so different here? Well, you see, the thing is that small w, which is what I call in physics, in chemistry, that this is the work done on the system, capital W is the work done by the system. These are opposite things in terms of the sign, which is why you get two different equations. They mean the exact same thing. Yeah, convince yourself of this. This is the first barrier you need to cross to be comfortable with thermodynamics. I know it's a lot of theory, but this life can be made a lot easier if you are sure that, listen, chemistry and physics have the same idea. Yeah? It's the same basic science. You can't get a different equation for the same law. That's not possible, right? So I hope I've driven that point home. I think that is literally the most important thing to start off with. From here onwards, things are very doable, yeah, in thermodynamics. You see, the work that you talk about is usually PV work, which is the pressure and volume work. You assume that the pressure is constant. So you get that the work is P delta V. Specifically, if you're talking about the work done in physics, it's P delta V. The work done in chemistry is minus P delta V. Why is that? Again, physics, work done by system. Chemistry, work done on system. Okay? These are the different things you need to keep in mind. So that's it. I've just explained the first law to you. Took me some time, maybe longer than it would have in a usual video that you see at BYJU'S on our app. Actually, we have some pretty cool animations. You should check it out. So yeah, back to what I was talking about. Work, right? So if you figure out work, heat, and internal energy and the internal conversions, you can solve any numericals based on these ideas. Yeah. So why did I spend so much time on the first law of thermodynamics? Because everything else is just a placeholder. Yeah? If you talk about, say, an isochoric process or an adiabatic process or I already said isochoric, isothermal process, all you need to do is keep one thing constant. You can figure out everything else, and the rest of it is basic math, which needs a little bit of practice. You'll need to do that. There's no way out. You need to work hard and then you get good results. That's the only way out. But in understanding the theory, which what I just told you, will go a really, really long way. Okay, figured out heat, figured out internal energy, kind of figured out work also, right? What did I say was very important about the chemistry way of doing things? I said there are two things I was going to do. First thing is, yeah, I proved to you that it's not different, chemistry and physics, thermodynamics. Secondly, I just proved to you that delta U is a state function. I also proved to you that Q and W are path functions. How? I took one path where I added only heat to increase the internal energy. I took another path where I used only work to increase the internal energy. So similarly, I could have many different paths where I have some work, some heat, a large amount of work, a small amount of heat to get the same final state, which is in terms of the internal energy, which basically proves that work and heat are path functions and internal energy is a state function. Yeah, because a combination of both of these path functions give you state function. Mind-blowing idea, I mean, if you think about it, right? I know that we mug this without really thinking of the consequences, but I think it's a very, very cool thing. Back to work, literally. So work done can be done in, say, many different ways, right? Many steps, so to speak. So if I want to get from point A to point B, point A to point B has some pressure and volume at point A, another pressure and volume at say point B, right? How do I get from there? I do work. I can do that in 1 step, 2 steps, 3 steps. I can do it in 10 steps. I can do it in infinite steps. So what is the meaning of infinite steps? When I do it in 1 or 2 steps, it's usually irreversible work. Yeah, I'm just running through a little bit more quickly now because I've explained the most important thing, which was the first law. Now, if you go to infinite steps, what does that really mean? Infinite steps means that each step is so small that the initial and the final stages of the pressure and volume are the same. Yeah, that is called reversible work. And yeah, with that you can pretty much solve any question thrown at you on using PV and T and all of those things, ideal gas law. So most of the first law is figured out with that. Yeah, so that's it. You're good to go there. What's next? What comes to mind? I'm going in the order that you would logically in a textbook, in a good textbook. So the next thing that I can think of is, I think, enthalpy. Yeah, that makes sense. Enthalpy was initially a theoretical idea which said that, okay, enthalpy is internal energy plus the PV work. Now, for a system that is not a gas, maybe say a liquid or a solid, internal energy and enthalpy are exactly the same thing. Because as I said, enthalpy is internal energy plus the PV work. But the change in enthalpy is not equal to the change in internal energy when you have gases, because there is PV work, right? That is a key idea here. Where is this enthalpy idea used? Mostly it's used to figure out actual reactions. Remember the burning of paper that I really shouldn't do because I have really important stuff written on it. If I burn the paper, I talk about combustion, right? So, and yeah, see, why I'm not explaining with the burning of paper as example is because it's such a complicated idea. See, if I burn this paper, sure, there's combustion, I can maybe use delta H ideas, but this is an open system. Yeah? I cannot have the conservation of mass. Carbon dioxide is formed, this is mostly carbon, hydrogen, and oxygen, and that escapes. So how do I apply just the basics of first law and things I've learned here? This is the idea I want you guys to appreciate. Yeah? This is why you're learning thermodynamics. Some of you may have this question that why do I even care about thermodynamics? You see, you can use some basic ideas learned here, apply them in some very, very complicated fields of engineering and medicine. If you take up chemical engineering or mechanical engineering or materials engineering, all of these things are very, very high-paying jobs. Yeah. So yeah, you could do that. Okay, back to work. Again, I'm going to stop cracking the joke. I'm sorry, that was the last time. I'm going to do that again. Okay, so delta H, as I said, is enthalpy, and you can figure out the heat of a reaction or the enthalpy of a reaction using the ideas of delta H. Now, the only thing you need to keep in mind there are a lot of equations for you to remember, right? That delta H of the entire reaction is delta H products minus delta H reactants and all of that. So, sure, practice these things. The theory that you need to know is from bonding, which is basically that if a bond is formed, energy is released, okay? And if I'm breaking a bond, I need to give it energy. So the difference in both of these, because every reaction is basically bond forming and bond breaking, the difference in these basically gives you the enthalpy of the reaction. This is the central idea to this. Once you have this, you apply Hess law. Hess law is basically arithmetic, right? I go from A to B. Now, to go from A to B, I can have 1 step or I can have 10 steps in between. Because enthalpy is a state function, it will give me the same result. That's all Hess law is. And yeah, if I reverse a reaction, the sign of enthalpy changes. So use these ideas and treat each reaction as an arithmetic equation, x plus y gives z, with some numbers, stoichiometric coefficients. And you reverse it, do whatever you want, and you can add and subtract them, multiply them with numbers if you need to increase the stoichiometric coefficient. Divide it with some number if you need some number if you want to reduce it. So simple, straightforward ideas. If you get questions on this, I think you must absolutely get those right. Yeah? With some amount of practice, that's really doable. So yeah, okay, I've covered delta H till now. Now, definitions are absolutely important. 2 important ones that come to mind right now, besides the usual ones, are bond dissociation enthalpy and bond enthalpy. Yeah? These are 2 different things. Go over them. Don't have the time to go over the definitions myself, but you absolutely must. Okay, so I've covered first law of thermodynamics. I've figured out delta H. What's next that's important? Quickly going over to entropy, things that most of us are scared of. If you see some videos or somebody explaining it, you can't give an example of, hey, why didn't you clean my room because, well, entropy, everything has to become more random. That's not an excuse. A lot of people use that as a joke. It's not even correct, because entropy has to do with energy and not really cleaning your room. Anyway, I won't go into the philosophy of what entropy is. You can read a good book to do that. I'm going to assume that you know what entropy is. And I'm going to try and make you appreciate the beauty of how entropy is different from everything else we've learned from till now. So entropy is one of those functions whose absolute value you can find out. The third law of thermodynamics says that at 0 Kelvin, entropy of a system is 0. That's the only time that's possible. So if I increase the temperature a little bit more, get some entropy. So how do I find, why did I say that it's an absolute value? If I want to find out the entropy of, say, this camera at this point in time, which is a really random thing to say, I know, the bad joke, random. Anyway, so yeah, if I want to find out the randomness or entropy of this camera, I just need to know its temperature, and I need to have integrate dq by t, yeah, minus integral of dq by t, and I get the change in entropy of the system, which is the camera. Sounds as ridiculous as it sounds, it's correct, yeah, where dq is basically the change in heat that was required to get this camera from, say, 0 Kelvin to whatever temperature it is at right now. I think it must be 24, yeah, 24 degrees Celsius is that. So this is interesting, which means that entropy would increase with temperature. Entropy also increases with the degree of randomness. You heard this many times, where it's actually the number of microstates. What do I mean by microstates? I won't go into detail, but basically, the way that things are arranged, if I go from, say, a solid to a liquid at that phase change temperature, a liquid has higher entropy. It has more microstates where the energy can be divided into. That's what microstates basically means in layman's terms. So these are two things you need to keep in mind, theoretically speaking. A lot of theory, I know, right? Thermodynamics is slightly difficult because there's so much theory. But if you read it like a good storybook, spend some time on it, you can solve literally any numerical on it. And the cool thing about thermodynamics is that this is applicable in equilibrium, in a little bit in electrochemistry and many other places, metallurgy as well. So this is a very, very important field. And as I said, if you decide to take up a core field like, say, chemical, mechanical, materials engineering, it's very useful there as well. So try and spend time on it. If you need help, hey, we are here. So is our app. So yeah, do that. Okay, back to delta S. Yeah, so I told you that delta S of a system is equal to integral of minus dq by t, dq being the heat change, right? Now, this may seem counterintuitive because I said that, look, when temperature increases, entropy must increase. But in the formula, I have dq by t. What does that mean? Remember, I'm integrating dq by t. So, even if q is not a function of temperature, which it usually is, even if it's not, even then you get q ln t, yeah, because integration is basically addition of very small parts. What does dq by t mean, the physical meaning of this? Look, if the body is at 10 Kelvin and I take it to 20 Kelvin, then the change is going to be much larger in entropy as compared to a system that is at 273 Kelvin and I take it to 283 Kelvin. That is what that dq by t means. Okay, this is an important idea. Try and do the actual math, put the numbers in, okay, and you'll get the same result that I did. So this is the idea of dq by t. Temperature, with increase in temperature, entropy increases, but if the temperature is high enough, then the change in entropy is lower as compared to a lower temperature. That's it. Cool. Now, all of the equations are for delta S of a system. That is something you need to really, really appreciate here. Why did I say this? Well, recently in a JEE exam, there's a question on that. It looked really scary to start off with. The question had 4 options, as most questions do. Multiple answers were correct. And the first part of each option had something to do with temperature and equilibrium constant. And the second part had to do with delta S system, delta S surrounding. It looks really scary to start off with. But actually, it's a really easy numerical if you just listen to what I have to say in the next minute or so. Right? The equilibrium part is really simple. Yeah, it's just a direct relationship between temperature and the equilibrium constant. You can figure that out. Now, it may be scary at the first look because in that question, delta S of surrounding was tested, and all the equations that we usually go through are delta S of system. The surrounding is often ignored, and it really shouldn't be. What does the surrounding usually mean? Well, the surrounding is something that is not the system. So if my camera is the system, then everything around it, which is me, these lights, and everything around is the surrounding. So generally, surrounding is very large. That's established. So what would be the equation if I want to find out the delta S value? Obviously, the Q value would be negative, right? Delta S system, whatever heat was there, the heat for delta S surrounding would be the negative of that. But in the denominator, the temperature is always going to be constant. The temperature of the surrounding does not change. That's why it's a surrounding. Yeah. In most cases that we will come across, this is the case. We do not have any complicated situations where temperature would change. So this is an important idea you need to keep in mind. One small part that I want to stress on is that this is about the surroundings. So just with this idea, you could have solved the entire numerical with the multiple correct answers. Back to the system, delta S of system, one small part that I want to mention is that when I talk about dq reversible by t, that's the actual formula, yeah? Integral of dq reverse minus integral of dq reversible by t. Why q reversible? Why did I say that? You see, delta S or entropy is a state function. So it doesn't care about the path that I took to get there. Yeah, I could do it in 1 step, 10 steps. It does not care. The physical implication of this, well, actually the mathematical implication of this is me putting q reversible over there. I don't care if the heat was added reversibly or irreversibly. But in the equation, I'm good if I use the q reversible idea because it gives me the same answer finally. That is a mathematical trick you need to use. And that's why this is q reversible. So yeah, I'm all done with the idea of entropy. What's next? I think what's really important now is Gibbs free energy. Oh wait, spontaneity. Hold on. Remember spontaneity? A system is said to be spontaneous if the total entropy of a system, wait, I said something wrong there. A system is said to be spontaneous if delta G is negative, right? What does delta S have to do with this? Well, delta G is delta S minus T delta S. You know this formula. I'm not going to go into detail of that. But there was something else had to do with entropy. What was that? Something increase, right? Entropy should increase in a spontaneous process. Well, here's the thing. The total entropy needs to increase, not the entropy of the system. Yeah, this is another place where students at times make mistakes. So it's delta S system plus delta S surrounding that needs to always increase. Yeah, that's another way of talking about the second law of thermodynamics. You know that there are many different ways to define the second law of thermodynamics, right? So this is one of those ways that the entropy of the universe always increases. So yeah, that's that. What about Gibbs free energy or delta G? When I was in school, I found this idea to be very funny, right? Someone's telling me that, okay, I understood internal energy. I kind of understood enthalpy also in school. But Gibbs free energy completely escaped me. Yeah, it was like somebody tells you, yeah, this is the amount of useful work that you can get out of a system. What does that even mean? I mean, somebody comes to you with that and asks you to solve the numericals. I could solve the numericals, sure, but what does that really mean? Well, this would be clear when you talk about electrochemistry. You see, when you convert the energy from a chemical reaction, what happens? You see, I have some reaction that gives out some enthalpy, some enthalpy value. I cannot extract all of that heat or delta H as work. That's what this Gibbs free energy comes in. I can only extract the amount, the value, actual value of delta G. That's why in electrochemistry, you get the equation delta G equals minus NFE. Yeah, F is Faraday's constant, N is a number of electrons that go on, and all of that. Yeah, E is the potential difference. So more on that later, maybe in another session. But basically, this tells you that this is the actual work I can get out of the cell. What is a cell? Another thing that completely blows my mind. You have chemical reactions that can produce electricity. You have electricity that can produce chemical reaction. That's what electrochemistry is about, right? So the work that you can actually get out of a system is basically that delta G value. Hence the useful work idea. Yeah, so I'm pretty much done with what I wanted to talk about. The practical example that I gave you was about burning paper. Now you see why that was so complicated? Well, to burn the paper, let me just run you through this. To burn this paper, I will need to light it, okay? And then there's some ash that's left behind because, well, it's not everything is organic. I may have some inorganic things in it as well. It's an open system. So to all of these things, even with everything we've learned in this small session here, and even through all the books that you would read in 11th to 12th, even with that, you cannot model the system in its entirety, yeah? Maybe with some ideas that you would learn in engineering, you would be able to design this burning the paper example. So I really thank my friend for giving me that example. It's a very cool example. I thought it was pretty weird for me to talk about this, but actually it was a good example to tell you guys how difficult it is to model a real system with the ideas that we know. I hope you will appreciate thermo as much as I do after this session. I'm going to try and look at a few questions that you guys have? Maybe just give me a minute. Okay, so I have a question saying, what is the oxidation number of zinc? That's interesting. Abhijit has asked this question. You see, the idea of oxidation number, although it's not entirely thermodynamics, I'm cool. I really like oxidation numbers and redox reactions as well. The idea of oxidation number comes into picture in an actual equation. Yeah. So zinc is a simple thing. Zinc usually forms a compound that has, say, it has a valency of 2. Say zinc becomes ZnO or something else becomes Zn2 plus, basically that ion. So the oxidation number in this is clearly 2. Generally, if you have something like chromium or something else, you could have multiple valencies. Yeah, so I would not be able to answer that question right away, like Abhijit asked me. But yeah, Abhijit's question is valid, and the valency is 2. And that's mainly because what happens with zinc is that it has a fully filled 3D configuration. Yeah, it's 3D10, 4s2. So those 4s2, they go away. Yeah, those 2 electrons go away, and you have the valency or oxidation number to be 2. And I hope that answers your question. Anything else? Any other questions? Wait, while my friend tells me what the question is, back to the most important thing I personally think is that you guys really shouldn't take any tension out of this. I know that's literally the worst thing to tell anybody who is tensed. There's a lot of time to go for the JEE. Yeah, it's December now. You have 3 or 4 months. Even if you start right now, yeah, if you go through what we have done on the app, even if you go through the kind of questions that we put up on our page every day, that itself will help you a lot, because most of the questions that come there are from the last year JEE exams, and we've put good solutions there. And a lot of these questions have been picked up from engineering textbooks as well. So I personally feel that if you subscribe to this channel and just check out a question every day. So we put up questions every day on chemistry, physics, and chemistry, physics, and math, and you'll be able to solve that. I have an interesting question. I'll just get to that in a minute. Hanuman Singh asked me, what is electrochemistry? Okay, I'll answer that right away. What is electrochemistry? It's a cool question, very philosophical. Electrochemistry is basically, changing of, if I have a chemical reaction, the reaction happens because that electricity is formed. That's electrochemistry. Or the other way around. Yeah, I zap chemicals and I cause, what happens if I zap chemicals? Redox reactions. Yeah, I cause redox reaction to happen, which means that something gets deposited, something else gets eroded or corroded. So I cause chemical reaction to happen because of electrochemistry, because of electricity. That's electrochemistry. So 2 things here. These 2 together, they are both opposing forces. I pass electricity through a solution, I cause chemical reactions to happen, or chemical reactions cause electricity to happen. Examples: electroplating is a good example of passing electricity and chemical reactions to happen. The other way around, if I have, say, your cell phone runs on a battery, right? So this battery has chemical reactions going on inside it, which give you the potential difference, which is responsible for the ions to flow inside your battery and gives you current. That is electrochemistry. Slightly off topic, but it's cool. I like this topic as well, so I can answer that question. Let me see, any more questions? Yeah, thank you for asking that question, Rohan Khurana. Can you explain different works done and how to remember them? I think you're talking about isochoric, isobaric, and all of those things. So my idea is, don't try and remember them. Remember what I spoke about for a large part of this session, the first law of thermodynamics. You see, I hope I didn't step on the mic. Yeah, why did I say this? And this is not a preachy thing to say. I'm very serious about this. Yeah, the only way to remember the different types of work is to solve numericals, and you don't need to remember it. You need to derive it. You'll be able to remember it if you solve a lot of numericals. Let me put it this way. But these numericals need to be from a good source. Yeah, this is a generic answer. I'll get back to the work thing. Yeah, but a generic thing is, don't just solve like 400 numericals on every topic and hope to get good at it. It could work for some people, but I personally think the most important thing is the theory. If you don't understand the theory, if you're just mugging numericals, if you're just mugging formulae, you'll only be able to get to a certain level. Yeah, I would call that maybe 60% of your efficiency. And I'm not making this number up. Yeah, I've had this experience. If you try and understand the concept, if you try and read a good book, that's personally to me the best way. And luckily for you, you have a better way. You have videos you can watch freely and also on our app. And these ways are so good that you can actually figure out to solve any tough numerical just from the concept. back to the idea of work, there are different types, right? Isochoric, isobaric, and all that. You need to remember the definitions and try and derive it. Yeah, I would suggest that maybe you need to learn one equation, for isothermal work, what the formula is. You have a log term, maybe that equation. More importantly, you need to know what the conditions are. Adiabatic means Q is 0, which means W should be equal to delta U. Figure out the signs. Yeah, I'm not stressing too much on that right now, but you should. Isochoric means what? Volume is constant. What does that mean? What is volume? That means no work is done, which means that delta is equal to Q. So this is what you need to get quick at doing. Make flashcards. Like say, write something on one side of the paper, write the answer on the back side. Yeah, and revise that. I think that would be a good way to memorize anything. But I would still say that try and go to the theory first. Friend had another question. Let me just take that out. What is the entropy change? That's a great question. So Shashank Aparna asked me, what is the entropy change in an irreversible process? So, see, entropy change in an irreversible process is also going to be dq reversible by t. Yeah, I know it's a little difficult to explain in the short time that I have. But what I explained to you was that, so are you asking irreversible or phase change? Let me just clarify both. Phase change is just Q by T, yeah? Because at that point the temperature is not changing, yeah? So I can just say it's Q by T. What is phase change? When you go from solid to liquid to gas and all that. There, pressure and temperature both are constant. Only then that equilibrium can happen, yeah, in a phase change reaction. So there, that part's clear. In an irreversible process also, the entropy change will still be equal to Q reversible by T or dq reversible by T, and that's a really important idea. Yeah, I don't have enough time to explain why, but read a good book or go through our app and our videos, and you'll be able to figure that out. Yeah. Okay. So how to solve problems on motors? What does Ankush say? Can you just a minute? Let me just figure out what Ankush is saying. I couldn't read the whole question. Yeah. How to solve problems on motors and heat loss? I'm not sure I completely understand the question, but I think, Ankush, you're talking about the physics part of it. If you're not, I apologize in advance, but if you are, you're talking about the second law of thermodynamics, right? So I mentioned that, okay, when heat flows, then there's a difference in temperature. Heat flows when you go from a high temperature to a low temperature. What do I need to do to get heat to go from a low temperature to a high temperature? I need to do some work on it. Okay, that's the idea of an engine or a Carnot cycle. That's if you're talking about that, a motor. So there you just have a direct formula. Yeah, the efficiency of an engine is 1 minus C2 by T1 and all of that. And that's the reason why you can never have a very, very efficient heat engine. Heat engine is somewhere where there's temperature change that's happening, right? I just told you why that is. That's because if you can never reach 0 Kelvin, you can never have a perfect machine. Now, most of, even machines that happen to be your bikes or your cars, the explosion happening inside them, the temperature difference is not high enough. I mean, even if it's really high, the maximum efficiency you get, I think, for a petrol engine is like about 40%. Yeah, I think about 40% or so. So yeah, that's the efficiency idea. I hope I answered your question. If I didn't, I apologize. From what I could understand, that was it. So yeah, I think that's all I have time for. I hope you guys enjoyed it as much as I did. I'm not burning this paper. Yeah, so I hope you guys had fun. Yeah, bye-bye.